Welcome to this overview of 5G policy control. In this video, we'll explore how policies are applied in real time within 5G networks. 5G policy control involves several key network functions that work together to manage services in the network. These include the session management function, policy control function, user plane function, and user equipment. The policy control function communicates with the session management function via the N7 interface, providing policy decisions that govern network behavior. The session management function then applies these policy decisions by communicating with the user plane function, which delivers the actual service to users. 5G policy control primarily focuses on two key areas: quality of service enforcement and dynamic charging rules. 5G policy control delivers several key benefits for both networks and users. First, it enables efficient resource management by optimizing how network resources are allocated. Second, it ensures a consistent user experience by maintaining service quality across different applications and network conditions. Finally, real-time policy application allows the network to adapt instantly to changing conditions and requirements. In the following sections, we'll explore each component of the 5G policy control call flow in greater detail. The Session Management Function, or SMF, is a core element within the 5G network architecture. The SMF serves as a central component that manages multiple aspects of the network's data sessions. One of its primary responsibilities is managing protocol data unit sessions, which are the logical connections that enable data transfer in 5G networks. The SMF interacts directly with the data plane, controlling how data packets flow through the network. A critical relationship exists between the SMF and the user plane function, or UPF. The SMF instructs the UPF on how to steer traffic and ensure packets are routed correctly. Let's examine the key functions that the SMF performs within the 5G architecture. The SMF manages user sessions throughout their lifecycle, from establishment to termination. It handles IP address allocation to user devices, ensuring proper connectivity. The SMF selects the appropriate user plane function based on various criteria such as load and location. Quality of service enforcement is another critical function, ensuring different traffic types receive appropriate treatment. Through traffic steering, the SMF directs data flows along optimal paths through the network. The SMF enforces network policies, working closely with the policy control function. Finally, it collects charging data for accurate billing of network services. As a central component in the 5G core, the SMF orchestrates how data sessions operate, ensuring efficient traffic management and proper application of network policies. The policy control function, or PCF, is a critical component in the 5G architecture. It serves as the central policy decision maker for the entire 5G network. The PCF interacts with multiple network elements to enforce its policy decisions. One of the PCF's primary functions is creating policy rules based on subscriber profiles and network conditions. The PCF governs control plane functions through policy rules, managing how network signaling operates. It also governs user plane functions through policy enforcement, controlling how data traffic flows through the network. To summarize, the PCF has several key responsibilities in the 5G network. It creates policy rules, determines quality of service parameters, enables dynamic charging, and supports network slicing. By centralizing policy decisions, the PCF ensures consistent application of rules across the 5G network. The N7 interface serves as the critical reference point for interactions between the policy control function and the session management function in 5G networks. This interface enables direct communication between these two essential network functions. The N7 interface utilizes modern web protocols, including HTTP2 and REST APIs with JSON data formatting. Various types of messages are exchanged over the N7 interface, including policy control requests, decision notifications, QoS updates, and charging rules. One of the key functions of the N7 interface is enabling dynamic quality of service adjustments. The PCF can instruct the SMF to modify parameters like bandwidth allocation, latency requirements, and priority levels in real time. The N7 interface is also essential for charging and billing processes. It enables usage monitoring, quota management, and real-time billing information to be exchanged between network components. The N7 interface provides several key benefits, including real-time policy updates, dynamic service adaptation, efficient resource allocation, and support for flexible charging models. Technically, the N7 interface is implemented as a service-based interface known as NPCF SM Policy Control, built on 3GPP standards for 5G networks. In summary, the N7 interface plays a crucial role in enabling the PCF and SMF to work together effectively, forming the backbone of policy control in 5G networks. During 5G session establishment, the session management function initiates policy control by sending a request to the policy control function. This policy request is the starting point for all policy control decisions in the 5G network. The policy request contains three critical types of information that the PCF needs to make appropriate policy decisions. First, it includes user information such as the subscriber ID, device type, and geographic location. Second, it contains details about the requested service, including quality of service requirements, data rate needs, and latency constraints. Third, it provides current network conditions, including congestion levels, available resources, and the type of access network being used. Let's examine how the policy request fits into the overall session establishment process. The process begins when a user equipment initiates a PDU session. The Access and Mobility Management function then forwards this request to the SMF. The SMF prepares a comprehensive policy request containing all necessary information. This request is then sent over the N7 interface to the PCF. Finally, the PCF receives and begins processing the request to determine appropriate policies. This initial policy request is crucial as it initiates the entire policy control process, allowing the 5G network to apply appropriate rules for service delivery. When the policy control function receives a policy request, it begins a comprehensive evaluation process to determine the appropriate policy decisions. The PCF first evaluates subscriber profiles, which include the user's data plan, subscription tier, and service permissions. Next, the PCF analyzes current network conditions such as congestion levels, available bandwidth, and cell load to ensure optimal resource allocation. The PCF also considers operator-defined policies, which include business rules, service priorities, and quality of service templates. Through this comprehensive assessment, the PCF ensures that policy decisions are context-aware and optimized for the specific conditions at hand. Based on this evaluation, the PCF generates context-aware policy decisions, including QoS parameters, charging rules, and traffic policies that will be enforced by the SMF. The Policy Control Function, or PCF, returns key policy decisions to the Session Management function after its evaluation process. These policy decisions contain essential parameters that govern how network resources are allocated to the user session. The PCF sends three main types of policy decisions: bandwidth limits, priority levels, and charging rules. Bandwidth limits define the maximum data rates for uplink and downlink traffic. These can range from megabits per second for basic services to gigabits for premium services. Priority levels, represented by QoS class identifiers, determine how traffic is handled during congestion. Higher priority traffic is processed before lower priority traffic. Charging rules specify how services are billed, including rating groups and metering methods like volume-based or duration-based charging. Policy decisions are tailored to specific sessions and users based on their subscription profiles and current network conditions. For example, a premium user might receive higher bandwidth limits and priority levels than a basic user, ensuring better quality of service for higher-tier customers. Here's an example of a policy decision sent from the PCF to the SMF. It includes session rules with bandwidth limits, QoS identifiers, and charging parameters. These policies are then enforced by the SMF on the user plane function to provide the appropriate service experience for each user. After the policy control function makes policy decisions, the session management function must enforce these policies on the user plane function. The policy control function determines policy decisions such as quality of service parameters, bandwidth limits, and priority levels. The SMF receives these policy decisions from the PCF through the N7 interface. The SMF then translates these policy decisions into specific enforcement instructions that the user plane function can implement. Next, the SMF sends these enforcement instructions to the UPF via the N4 interface, which is the control channel between these two functions. The UPF then implements these instructions to enforce policies on the user data traffic flowing through the network. Let's visualize how data traffic flows through the UPF with policy enforcement applied. As data packets flow through the UPF, they're subject to various enforcement mechanisms such as traffic shaping, QoS implementation, and packet filtering. The UPF implements various enforcement mechanisms based on the SMF instructions. These include bandwidth control, QoS implementation, traffic filtering, and deep packet inspection. In summary, the SMF plays a critical role in enforcing policy decisions on the UPF. This ensures that data traffic adheres to policies set by the PCF, effectively controlling how network resources are used and providing consistent service quality. 5G brings a revolutionary approach to network architecture called service-based architecture, or SBA. Let's compare traditional network architecture with the new service-based architecture approach. In traditional architecture, network functions connect through point-to-point interfaces, creating a complex mesh of connections that's difficult to scale. In contrast, service-based architecture uses a common service bus with standardized APIs. Network functions can easily communicate with each other through this central interface. SBA enables network functions to communicate using REST APIs, which are the same interfaces used in modern web applications. When one network function needs information from another, it sends an HTTP request through the service bus. The request is processed and a response is returned with the required data. This REST-based approach offers several benefits for 5G networks, including stateless communication, language-independent interfaces, and simplified implementation. In 5G networks, the policy control function, or PCF, and the charging function, or CHF, are key components that benefit from service-based architecture. These functions interact via open REST-based interfaces, allowing them to exchange policy and charging information seamlessly. This SBA approach provides several key benefits for policy control in 5G networks. In a complete 5G network deployment, all network functions connect to the central service bus, enabling flexible and dynamic communication. The interaction between PCF and CHF is particularly important, enabling real-time, policy-based charging decisions that enhance service quality and monetization options. Looking to the future, SBA will continue to evolve, with cloud-native implementations, AI-driven policy decisions, and integration with edge computing services. In a 5G network, the policy control function, or PCF, plays a critical role in the policy control flow. Under normal operation, the PCF provides optimal policies to the session management function, or SMF, which enforces these policies across the network. However, if the PCF becomes unavailable due to network failure, maintenance, or other issues, this disrupts the policy control flow. When the SMF detects that the PCF is unavailable, it applies default policies stored in its local configuration as a fallback mechanism. While this ensures service continuity, these default policies are typically more generic and less optimized than the tailored policies that the PCF would provide. This can lead to suboptimal resource allocation, where network resources aren't utilized efficiently, and service degradation, potentially affecting user experience until the PCF is restored. Within 5G policy control, invalid policies present a significant challenge. The policy control function, or PCF, is responsible for generating policies that the session management function, or SMF, must interpret and enforce. When policies are valid, they travel through the N7 interface to the SMF, which then applies them correctly. However, sometimes the PCF may generate invalid policies that the SMF cannot interpret or enforce. When an invalid policy is transmitted to the SMF, it cannot be correctly processed. There are several types of invalid policies that can cause issues. These include malformed QoS parameters, contradictory charging rules, unsupported traffic steering directives, and incorrect subscriber data references. The consequences of invalid policies can be severe. These include session setup failures where connections cannot be established, service degradation affecting quality, inconsistent user experience, and incorrect charging for services. To address invalid policy issues, networks implement several measures. These include policy validation by the SMF, using structured policy templates, protocol conformance checking, and comprehensive error handling mechanisms. Recovery options, retry mechanisms. Retry mechanisms are a common recovery option when the session management function cannot get a policy decision from the policy control function. In a normal scenario, the SMF sends a policy request to the PCF over the N7 interface, and the PCF promptly responds with policy decisions. However, sometimes the PCF may be unavailable or fail to respond to the SMF's policy request. When the SMF fails to get a policy decision, it can implement a retry mechanism. After a short delay, typically around 100 milliseconds, the SMF will retry the request. The first retry attempt sends the same policy request again, hoping the PCF has recovered or the network condition has improved. If the first retry fails, the SMF implements exponential backoff, doubling the delay time before attempting again. This progressive backoff strategy prevents network congestion from too many rapid retries while still attempting to recover the connection. After several retry attempts with increasing delays, the SMF eventually succeeds in getting a policy decision from the PCF. Upon successful connection, the PCF provides the policy decision and normal operations resume. Retry mechanisms offer several benefits for 5G networks. They improve system resilience, handle temporary network issues, minimize service disruptions, and are relatively simple to implement. When implementing retry mechanisms, several factors must be considered: maximum retry count limits, exponential backoff to prevent network congestion, appropriate timeout values, and fallback policies for when all retries fail. Recovery options. PCF failover provides critical redundancy in 5G networks. In the 5G architecture, the SMF communicates with the PCF to retrieve and enforce policy rules. Under normal conditions, the SMF communicates with the primary PCF to retrieve policy information, which is then enforced on the user plane function. However, the primary PCF can become unavailable due to hardware failures, network issues, or scheduled maintenance. When the SMF detects that the primary PCF is unavailable, it initiates a failover process to switch to a backup PCF. The SMF then connects to the backup PCF, which provides the same policy control functionality as the primary PCF. PCF failover ensures continuous policy control, minimizing service disruption for users. This redundancy is crucial for maintaining quality of service in 5G networks. Technically, PCF failover maintains the N7 interface with a backup system, transferring session context seamlessly. Network operators configure detection parameters to optimize failover speed and reliability. With PCF failover in place, the 5G network maintains reliable policy control even during component failures, ensuring that services remain available and policy compliant. When recovering from policy control issues, the SMF can resynchronize policies from the UDM. Several situations can trigger policy resynchronization: when inconsistencies are detected after a PCF failure, when subscriber policies are updated, or during scheduled network maintenance. The resynchronization process begins when the SMF detects a policy inconsistency. The SMF sends a request to the UDM to retrieve the latest policy data. The UDM responds with the latest subscriber policy data. The SMF updates its local policy database with the retrieved information. Finally, the SMF enforces the updated policies, ensuring all network functions operate with consistent policy data. UDM policy resynchronization offers several benefits. It ensures policy consistency across the network, reduces recovery time after failures, provides a reliable fallback when the PCF is unavailable, and helps maintain service quality during network disruptions. When implementing policy resynchronization, operators should consider rate limiting to prevent UDM overload, prioritization of critical subscribers, scheduled bulk resynchronization during off-peak hours, and proper validation of retrieved policies before enforcement. In summary, UDM policy resynchronization provides a robust recovery option when policy inconsistencies occur in the 5G network, helping maintain reliable service delivery. Policy control provides significant benefits for network operators through efficient resource management. In a 5G network, the policy control function and session management function work together to optimize how network resources are allocated. Dynamic policy control enables operators to adjust quality of service and charging rules in real time based on network conditions. Without effective policy control, network resources may be inefficiently allocated, leading to wasted bandwidth and processing power. By dynamically adjusting policies, operators can optimize resource allocation, significantly increasing network utilization. Policy-based resource management delivers three key benefits: optimized network utilization, dynamic QoS adjustments, and differentiated service delivery. This approach significantly improves resource utilization metrics, increasing from approximately 58% to 89% in typical deployments. With efficient resource management through policy control, operators can handle more traffic, deliver better service quality, and create tailored offerings for different customer segments. 5G policy control provides significant benefits for users in the form of a consistent service experience. Users subscribe to different service tiers, each offering specific levels of quality and performance. Basic subscribers receive standard quality of service with best effort delivery. Standard subscribers enjoy enhanced performance with priority data handling. Premium subscribers benefit from guaranteed service levels with maximum bandwidth. What makes 5G policy control particularly valuable is how it maintains consistent service across varying network conditions. During normal conditions, all users enjoy optimal service. But when networks become congested, policy control ensures that subscribers still receive appropriate service levels relative to their tier. Let's look at the specific benefits users receive from consistent policy control. Policy control ensures tier-based quality assurance, consistent performance, and predictable bandwidth. It also enables adaptive resource allocation, fair usage during congestion, and application-specific priorities. To illustrate this, let's see how different users experience video streaming under the same network conditions. Each user receives bandwidth appropriate to their subscription tier. Basic users stream in standard definition, standard users enjoy HD content, while premium subscribers experience 4K quality, all simultaneously and consistently. Through effective policy control, 5G networks ensure that users receive a consistent service experience aligned with their subscription tier, regardless of changing network conditions. As 5G networks scale to support millions of devices and diverse use cases, policy control systems must evolve. 5G policy control must be highly flexible and agile to manage increasingly complex networks with diverse requirements. The variety of connected devices in 5G, from IoT sensors to augmented reality headsets to autonomous vehicles, each require different policy handling. Policy control systems must be flexible enough to handle different strengths, quality of service requirements, service prioritization, and dynamic network conditions. Automation becomes essential as 5G networks face orders of magnitude increases in signaling traffic compared to previous generations. With 5G, operators need to plan for at least 2 orders of magnitude increase in signaling traffic. This volume makes manual policy management impossible. Automated policy control delivers significant advantages over manual methods, providing consistent experiences, rapid adaptability, and the ability to scale with network demands. Each 5G use case presents unique policy requirements. Enhanced mobile broadband needs high bandwidth. Ultra-reliable communications demand minimal latency. Massive IoT requires efficient handling of numerous low-power devices, and connected vehicles need dynamic quality adjustments based on changing conditions. To succeed with 5G policy automation, networks require AI-based predictive decisions, closed-loop optimization, standardized interfaces, and edge computing integration for latency-sensitive applications.